Now, we've gone through some of the topics for Chapter 17, but I would like to take a few minutes and just say some of the things that you could do so that you would succeed better on the tests. So some people understand the ideas, but they just don't do all that well on the tests. So let's see what we can do. First thing is, when you see a problem, look for the H plus and the OH minus concentrations. That's what we need to do. Maybe change the acid concentration into H plus. Look and see if it's diprotic, just different things like that. But focus on the H plus, OH minus concentrations. Another thing is you've got to get really good at these icebox problems. You need to be able to just do those naturally and quickly without a lot of thinking. Another thing is, as you're going through these problems, pay attention to what X equals. So when you get done, is X equal to the H plus concentration or is X equal to the OH minus concentration? Because that will totally change your answer. Look for twists in the problems. So if we go through something kind of a standard way, well then what if we leave out something unusual and you have to solve backwards? That's not a big surprise in a question like this. Okay, and the last thing that you can really do here is go back and practice, practice, practice. Now you can practice with questions from the book. You can practice with questions from your review book that you purchased for AP. You could go online to the M HBr and look for the Nacho questions and practice those. But the more you can practice, the more you learn how to do problems. Now I'm going to show you a couple of different problems, about 8 different problems, and for each one of these I'd like you to do is to kind of stop and try the problem yourself and then run it and let it I'll go through the answer. So stop for a moment and look at this question. Now this question is a pretty standard sort of a question. So it's saying what's the pH of a solution of HBr, and we should say okay, that's a strong acid. So again, we are really concentrating on the HBr the H plus concentration. So since it's a strong acid, the concentration of HBr is the concentration of H plus, so we just need the negative log of this number. So now we know that since it's 4.2 times 10 to the minus 4, then that is somewhere between 1 times 10 to the negative 4 and 1 times 10 to the negative 3. So we need a pH that's somewhere between 3 and 4. In that case, we can eliminate that answer, we can eliminate that answer, and we can eliminate that answer. Now, if you were guessing, you'd guess either B or C, but you really would calculate the answer and find out the answer is B. Okay, look at this question for a moment. Now we're talking about the pH of a base, KOH. So the first thing we should do is say, okay, the pH is definitely going to be greater than 7, so you can eliminate those two answers. Now, we go back and say, this 0.02, we can think of that as 2 times 10 to the negative 2, and when we take the negative log of that number, and we can do it in our head, we're going to get the POH, and we have to subtract from 14. Well, we can see what happens here. There's no way that this is the right answer, okay, because that would be times 10, 1 times 10 to the negative something. So the answer has to be answer A, 12.3, even without a calculator. Okay, look at this question for a moment. Okay, when you try this, you might notice that this is a really standard icebox problem. So we have HCN, double arrow, H plus, CN minus, and we have our initial concentration, 0.01. This is 0, minus x plus x plus x, x, 0.01 minus x. And this value is pretty small compared to our initial value. So we know x is going to be small enough to ignore. We're going to subset that into the Ka expression. So when we can see that this is just plain old standard icebox problem, then we want to go back and say, okay, we can actually do the shortcut here. Now the shortcut, you should get good at this, is the idea that the x, in this case the x is going to be our H plus concentration, is equal to the initial concentration times the Ka. Now at this point we can actually do this in our head. 0.01 times 6.2 times 10 to the negative 10 would be 6.2 times 10 to the negative 12. Square root of 10 to the negative 12 is going to be 10 to the negative 6. Square root of 6, well, we know the square root of 4 is 2, so it's going to be 2 point something. And we can see that the only answer that looks good is answer B. So 2.5 times 10 to the minus 6. So again, we can solve this calculation without a calculator. Okay, go ahead and look at this problem for a moment. Now when you look at it, you see this actually sort of like a standard icebox problem, but the thing here is this is one that has a twist. So normally what we would do is say, here's the initial concentration, here's the Ka, let's calculate the H plus concentration. But in this problem, we're given the H plus concentration. So we know this value, we know this value, we have to solve for the Ka. So now at this point, we're just going to substitute numbers in, and it's an algebra problem. And the answer I've calculated, I actually got 6.48 times 10 to the negative 5. So I'm eliminating these three answers. So I think the answer is C. So I'm not sure whether I made a calculation error or whether there's an error in the problem. Go ahead and look at this for a moment. Okay, we're going to say who is not a conjugate acid-base pair. So now we're doing process of elimination, and the idea is pick out any one that is a conjugate acid-base pair. And we know that the conjugate acid-base pair is going to be different only by an H+. So this one, we can eliminate this answer because we can see that the only difference here is an H+. Same thing with this one and the bottom one. Okay, each of these two are only different by H+. This is our answer because it's actually different by 2 H+. So it is not a conjugate acid-base pair. Okay, take a moment and look at this. Now this has a couple of different ideas in the same problem. First, we're saying that the K is less than 1, so we're supposed to know that that means that this is reactant favored. And if we try to rewrite our equation, we would say we have lots of HCN at equilibrium, we have lots of bicarbonate ion at equilibrium, and very small amounts of CN minus and carbonic acid. Now, we've learned that equilibriums always favor the weaker acid, weaker base. So we're looking for the stronger acid, stronger base. That means we want one of these two numbers here, one of these two values, and we just figure out which one is a base. So we can go back and say, this is an acid, so this must be its conjugate base. Okay, this is a base, this must be its conjugate acid. So we can see that Cn minus has to be the right answer. So it's asking, do we know an acid from a base? And can we tell which one is stronger and weaker, given the clue that K is less than 1? Look at this problem for a moment. Okay, this is a pretty straightforward problem. And the idea is, if we want the conjugate acid, then this must be a base. If it's a base, then it's going to be a proton acceptor. And if it accepts a proton, it becomes H2CO3. So that's the answer we're looking for, H2CO3. That would be the conjugate acid of this base. Now, if it had asked for the conjugate base, then this would be acting like an acid, and it would donate and would become CO3 2-. So this would be the conjugate base of our substance. But this is our answer. Okay, one last problem. Take a minute and look at this. Now, this is telling us to use the information that we understood before. So this is a good problem that separates the people who memorize things from the people that really understood why they were what they were. So we learned that the pH of pure water is 7.0, and that's not going to be true in this case because we said at 25 degrees, the kW is 1.0 times 10 to the negative 14. So how do we get the H plus concentration? We take the square root of that number, and that's 1 times 10 to the negative 7, and then the pH was just the negative log of that value. So that's where we got the 7. So that's why water under normal conditions has a pH of 7. But now that we've changed things, okay, we'd have to do the same thing. We'd take the square root of 1.2 times 10 to the negative 15 at 0 degrees, and then once we get that answer, we would take the negative log of that value. Now if you go through all that trouble, it turns out to be 7.46. And that's all we have to practice right now.